Glory and honor to our Lord and Savior Jesus Christ. I'm Salvador Cordova. Welcome to the Evidence Reasons Academy, a sister channel to the Evidence and Reasons for the Christian Faith video channel. This is the academic channel where we bear the cross of having to learn college and graduate level science so that we can understand the creation evolution controversy. We also cover just other varieties of topics that are relevant to just being a well-rounded scholarly individual, commenting on things about the Christian faith. And apologies for about the hour-long delay trying to get the show on the road. I was frantically dealing with some household problems like a woodpecker. That was unpleasant. So I'm still dealing with the woodpecker. And also I was going through, it's been 30 years, guys, since I studied electromagnetic theory. And this is not for the faint of heart or putting brain to mind. This takes dedication, and it's a cross to bear. So I've been slugging through it, and I'm realizing sometimes a lot of things are confusingly taught in the textbooks and also the internet pages, and you try to synthesize it. I'm not saying that this is some conspiracy. It's just a difficult topic, and a lot falls through the cracks. Even now, looking through my book, it's amazing anyone learns anything, because there's some things that could have been far better explained, such as electric flux in one part of Maxwell's equations, because it has a fluid model. It's just really funny that until you actually work through the math, it's like there's no charge density there, at least in terms of physical particles. It's a flux density. Just little things like that start to add up. And let me see if I can actually find the equation, because we actually covered it a little bit in we covered it a little bit in the last round. And they're just some this book is just, it's just full of stuff like that. It just, you just like, that there's nothing really, there's like hardly a single page that is trivial. It's all like that. And I remember studying this, it'd take me like 4 hours to get through. But it helps the modern world move forward. Without our modern understanding of electromagnetic theory, we would not have the modern world. And I'll show you. This is Maxwell's first equation of electrostatics. And let me show you. Do you see that where it says div D equals rho? That's called rho V. Equation 20 there, aptly called the point form of Gauss's law. This, in greetings, gangsters ghost, this was just absolutely miserable trying to understand this, because this rho V is supposedly charge density. See, it says that the volume charge density on the right, that's not really a charge density. Meaning, when I think of charge density, I think of electrons and how packed the electrons are. And Maxwell's equations is really a fluid model, the classical model. Even though Maxwell was a pioneer of atomic theory, his equations were not necessarily discrete. It modeled it at the macro level as a fluid, a continuous fluid, rather than something composed of many particles. And even when you could have like a charged sphere, and then you had the charged field radiating an electric field outside of that charged sphere. The area that had no charge, that was kind of just like air or a vacuum, it technically has a charge density. So this is what I began agonizing over that. And if I'm misstating this, guys, feel free to try to explain, because when I work through this, when I do the divergence of the electric field at points in space that are far outside that charged sphere, I get a rho v, and I said, okay, this, I mean, people who are familiar with Newton's shell theorem would understand sort of, I guess it's kind of a reverse of it of some sort. When I was working the math through this, I'm just like, how are you getting a rho v there? There's nothing there. I mean, except vacuum and an electric field. There's not a physical, there's like not physical electrons there, so to speak. So I'm just pointing that out, guys. All right. And I remember I could see it's just a miracle that any of us get through this. And then last week we covered, the last time we did this, we were covering, let me bring it up. I have, hang on, guys. I have my computer here, my other computer screen here. And I was going through like the fact that you can start off with a vector field, no, a scalar field. You apply a gradient and then you end up with a vector. But it's a little bit funny having it's a little more subtle than that, because I need to draw up diagrams to show we have what we call domain and codomain, or in the olden days, domain and range. I like domain and range because it makes it a little bit more distinct. So when you say x is the domain, f of x maps to the range or codomain. And that's how, thing with functions, mathematical functions. F of x is some equation dependent on x, what we call a function of x. And so you a lot of times, just normally for most physics applied type math, you use the real number line. So you start with the number on the real number line, and you call that, like, you represent it with a variable x. And then you have some formula that involves preferably only x. Just for simplicity's sake, let's just say you start off with an equation that involves x and only x, just for starters here. Then you would create something called f of x. So that formula gives you another number, and we call that number f of x. And sometimes we represent it by y. It's nicer to call it f of x if you want to be a formalist, because when you get up to higher dimensions, it becomes hard to just do something like where you put f of x on the y-axis, and it gets really bad when you're mapping 4 dimensions into when you're starting off with your instead of just x, you have x, y, z, and t, and then you're mapping it to something else. It just gets really messy. You can't, the human mind cannot visualize it in spatial terms. It's just purely abstract. I remember doing something in General Relativity, which is, again, a long time ago now. And it was X, Y, Z, and W. And I'm just like, I cannot comprehend this visually. You can only do it in mathematical abstractions. It defies anything in human experience when you have that many dimensions. And so, where was I? So we're talking about I lost my train of thought. So we were talking about electromagnetic theory and the divergence, and then scalar fields and vector fields. Oh yes. So with a gradient, you actually start with an XYZ as your domain, and then your range ends up being another. You have an XYZ that in an XYZ point associated with that point is a quantity. So it goes, you could say, let me see, it's a scalar field. Okay. The problem is with vectors, you have magnitude and direction, but many times when you just have a point in XYZ space, it looks like a vector when it's really just a point. Okay. The representation is unfortunately this tuple, this triple. Where you say XYZ, is the XYZ a vector or is it just a point in space? For a scalar field, you have an XYZ and then an associated value with that XYZ. So at point XYZ, you'll have a real number at that point. And it's like, okay, this isn't a vector, it's a scalar field. So at every point every XYZ point in that space has an associated, say, intensity. And it gets really confusing when you're dealing with XYZ the point, or if you're thinking this is like kind of like XYZ is a vector. It's not quite that, because they try to distinguish it with the IJK. And you can actually see that here. And this is where it gets really confusing. A scalar function of position R. So the position is XYZ and it maps to a value U. So you could say then the domain is in 3 dimensions, XYZ, what we call R3, R being real and 3 being, the 3 dimensions of a 3-dimensional space using real number coordinates that are in real numbers, XYZ. And then that maps to R1, which is just the real number line with just one number. So you have something with 3 coordinates that maps to one number. It's a funny looking kind of function. I don't know if I guess you could call it a function. And that creates a scalar field. So it's a scalar field. And then what you do is you apply this thing called a gradient, where you take all these partial derivatives, and I'm looking at it here, and then you map that scalar field to a vector field. Now, I didn't academically cheat. When I say I cheat on this, sometimes you don't really understand what you're doing. You just kind of go rote through through kind of the mechanics, kind of the machinery of what the professor says. He said, just take the gradient of this, and just like, okay, I could do that mathematically, but I have no clue what it is representing physically. And that can become extremely confusing And so I got through a lot of school where, okay, I was adequate enough with the math and just the calculus, but I'm just like, I have no clue what this thing describes physically. I'm just going through the motions and good enough to do the homework, good enough to get through the tests, and sometimes and oftentimes get an A, but I'm just like, if you're asking me how this applies physically and to try to visualize it like I was in some of the math classes where they really went through a little bit more trouble to try to describe things, and try to say, okay, this is easy to comprehend, or this is not so easy, or it's impossible to comprehend except only in abstract symbols, because there's nothing in everyday experience that we can use to make a real good analogy to this. So I might have to kind of munch on this, where you go from kind of three-dimensional space that maps to a one-dimensional space, quote unquote. And then you take those, that creates a scalar field. Those two somehow creates a scalar field. Maybe one way to describe it is if temperature. So if you're going like across the solar system, at every point in the solar system, you could measure the temperature. There's if we could hypothetically say there's an XYZ coordinate system around the solar system, we can go around and have a hypothetical thermometer, and we would be able to get a temperature reading at each XYZ point. The formalism of this is kind of ugly, but intuitively, that's almost, that's one illustration. But you could see me fumbling trying to describe the formalism of this. It's not nice. It's very nice when, okay, so let's say we have the distribution of temperatures across the solar system. You could have a huge database, and you could, in principle, create what we call the gradients of this, of how the temperature is decreasing at one point versus another point. So like if you're going from the North Pole to, say, the equator, you have a gradient of increasing temperature. In electromagnetics, a lot of those points in XYZ space it's desirable, can be summarized by an equation. So the nice thing is you might have one nice equation, like say the electric field from a point source is very nicely described. So thank you, Dr. Joel. So the math, you can have one equation that describes throughout a very large space, or hypothetically infinite space, hypothetically kind of in an abstract sense. And then from that, you can apply all of this math machinery to create these things called like gradients. So you have this scalar field, and you can kind of see it like when you generate a static field, like with the hairbrush on a cold, dry, wintry day. As you bring the hairbrush closer to some, like your hair, it'll start to attract it more. And the closer and closer it gets, the stronger the attraction. The farther it gets, the weaker the attraction. You can approximate that by an electric field equation. It's nice if you have something that's spherical as your electric field, because the equation for that is nice and simple and symmetric. Those are the kind of equations you really want to work with. You can then take that and apply this gradient formula, which you see here, and then you'll create, so you apply the gradient to that scalar field, and you'll generate a vector field. So what would a vector field from a point source look like? It just occurred to me. So let's see. If you'll indulge me one moment here, I'm going to look up something. See. There is a beautiful picture of this. Electric field from a point charge. Will indulge me. No. So, and there you go. Electric field from a point charge. That's the intensity of the electric field. You can also put vectors on that. So that is the electric field intensity. If you put this in vector notation, you just simply use the R vector. So that's the other thing in electromagnetics. You have basically three coordinate systems that are heavily in use. There are other ones, but the most standard one is XYZ. But there's also the cylindrical coordinate system, and the cylindrical coordinate system I'm not very familiar with. Cylindrical is R or rho. I prefer R. Z and phi. And then you have the spherical coordinate system, which is R. I like R, theta, and phi. So when you're describing the globe, theta sort of corresponds to latitude and phi to longitude. Did I get that right? Longitude. And R is the radius of the Earth. Usually you approximately make it the same fixed radius. It's not exactly, because I think the Earth is an ellipsoid. But you try to use the coordinate system that kind of makes everything symmetric so that the math is easier. So here you would not use XY coordinates, XYZ coordinates. You would use spherical, which is R, theta, and phi. And maybe I can, if I'm lucky, I could find the page that actually dealt. It started to show just how give me a moment here. It was showing, right, okay. I'm going to show you, so that equation, you see this EKQ over R squared. The K can be described as 1 over 4 pi epsilon naught. I'll show you how it's stated in my electromagnetic theory book, equation 10, in spherical coordinates. Look at equation 10 there in spherical coordinates. If you replace 4 pi, if you take 1 over 4 pi epsilon naught, that equals the K in here. So that K, you just substitute with 1 over 4 pi epsilon naught, and you'll get that equation 10. That's if you're using the unit vector AR. Unit vector being, 1 unit in the radial direction. Again, so if we're looking at a globe, like say a sphere, that would be the radius of the Earth. Or, if you're looking at the orbit of satellites, it's the distance from, the satellite's distance from the center of the Earth. I'm sorry, I'm struggling a little bit to describe this. I don't have quite all the props. and I'm kind of processing it in my mind. One reason that I'm doing this is it's also teaching me, and it's going to help me to teach it better. I think I mentioned before that I started college as a declared physics major. The fact I never finished the calculus series tells you all you need to know about why I'm a biologist now. Well, thank you, Dr. Joel. So I'm sorry we're struggling through the basics here, but this will all lead to special relativity and then the complications it presents for people arguing for a young universe. And then also we're going through this because Russell Humphreys is going to be here to talk about geomagnetism on Wednesday, and we're going to need lots of Maxwell's equations. And we barely got through the first, the point form of Maxwell's equations. But what I want to show is look at equation 11. Equation 11 is equal to equation 10. Equation 10 is written in spherical coordinates, which is r, theta, and phi. Equation 11 is written in Cartesian coordinates, x, y, and z. And you could tell that the form of the electric field equation is nasty in Cartesian coordinates. It's nasty. I wouldn't want to be having to do partial derivatives on equation 11. That's going to be nasty. Partial derivatives on equation 10 is not so bad, is it? So we can have a, let's see, what would be the partial derivative of that with respect to r? I think that's doable. In equation 10. And I'm going to embarrass myself, but I think it's going to be something like r cubed. Did I get that right, guys? Or am I doing that backward? You know what? I'll tell you how to do this so I don't screw up. We have what we call Wolfram alpha. So let me put up Wolfram alpha. So when in doubt, pull the calculator out. Let's see. Calculus and analysis. Integrals, derivatives. Derivative of 1 over r squared. 1 over r minus 2r cubed. Okay, I was right. So if I wanted to take a gradient of that equation, and I really would like, I wish I had if I wanted to take the gradient of this equation of a vector field, if I wanted to take the gradient of a scalar field that had that form, assuming it was a scalar field, it would be easier. But I just realized something. I shouldn't have done that, because you don't take gradients of electric fields. Duh. Some of you sharp guys out there know I just made a big mistake. You take gradients of a potential field, because a potential field is a scalar field. In that potential field, we call it voltage. So there's an example of a potential field. Okay, so, all right, I'm really fumbling through this, guys. Forgive me. This is good. This is good for my soul. Once upon a time, someone said everyone should study Maxwell's equations because it's good for the soul. Okay, so there is a equation 15 is the voltage from a point charge. So if you just imagine like a little point, the voltage from that point is just based on that equation. You can then take the derivative of that, and I'm going to, since this is a homework exercise, I'm going to cheat. And so let me just try to enter how this would be. Q. I'm just going to use 1 over R. Let's see how it processes that. I don't know how I can get it to describe if I put other things like, say, Q. Derivative. With respect to R. I don't know how to put the other stuff. Hi, Ben Rex. I'm doing a homework session trying to understand this. Actually, maybe you can help me. Okay, I want to differentiate with respect to R. That's not too hard. But when I put Q, I don't want it to do it with respect to Q. I want it to do it with respect to R. So let me look at examples. Maybe the examples. D dx. Okay, let's try this. Let's try d dr. Good. That's what I wanted. There. Okay, so for a potential field, we have 4 pi. I don't know how to do these blasted Greek symbols. 4 pi epsilon naught. 4 pi. There we go. So I'm trying to, I'll show you what I'm trying to do. I'm trying to create the gradient of a scalar field. And this is from my electromagnetic theory book. 4 pi epsilon naught. So it'd be minus q r squared. So there's this gradient operator. There's a gradient operator. Oops. Here. And if we use cylindrical coordinates, the last two terms under spherical are dropped. They basically zero out. And then all you have is the unit vector AR times this. And you're able to get the gradient. Okay, so I've been just really fumbling through electromagnetic theory here. All right, that's enough agony, I think. Oh, we've only been doing this for 36 minutes. So going back to oh, those sirens are annoying. Yes, they stay the same. No, yes, they do. And so you could see it here. The derivative is exactly as you say. But, you know, one reason I put things through alpha is it's been a long time since I've just been doing all the rote math. And it's easy to get like a sign wrong or just, you know, add one when I'm supposed to subtract or vice versa. So, yes. So it's nice that it did it this way. It did the partial derivative with respect to r of this 4 pi epsilon r. It's actually epsilon naught. I think I can, let me see if I can cheat here. See if I can even improve the notation. No, it didn't. It's supposed to give me a subscript, not a zero. It's just kind of a notate. Yeah, the notation in Wolfram alpha is different. So I can't really put the 4 pi epsilon with the zero subscript. But you can see the partial derivative of all this is equal to that. And that's really nice. So whenever I'm doing the math, whenever I'm doing the math and I'm in doubt, I could, you know, unlike in the olden days before Wolfram alpha, I had to do this by hand and hope and pray. But now, you know, if I can do it by hand, but I can also cross-check it now. So I can do the partial derivative of this and get that. So professionally, I mean, at this point is, you know, even someone as smart as John Gideon Hartnett, when he's doing physics work, he'll try to as much as possible to use stuff like Wolfram because it'll get it standard right. Now, there are some calculus things that just blow up Wolfram. And there was one integration that my professor tried to have all the students do. None of us could figure it out. I was pumping it through Wolfram. I was decomposing. I still could not. And then there was one integral in an astrophysics class. It looked innocent enough, took 8 hours, even with Wolfram. It was just miserable. And I'm just like, okay, I'm in an astrophysics class, not a math class. I mean, to him, everything's math. He's a mathematical type physicist. A lot of these physicists are closet mathematicians. You know, Michael Faraday was more of like what I would consider a true experimental physicist. He did not really have a lot of the math. He had a lot of kind of the intuitive insight. So anyway, that was, you know, what ends up happening is what I was showing with all the partial derivatives is when we're doing electromagnetic theory, I mean, this is really ugly to do stuff like this. But if you have Wolfram alpha, let's say you have the equation for V, which is the voltage, the potential field. And it's really nice. You have the voltage there and the voltage there. When you're solving electromagnetic equations, if you have the function for V, you can do it by hand for practice. Excuse me. Let me try to get this back in focus. You can do it by hand for practice, but you could just pump it into you can pump it into Wolfram alpha. You could put V in there and it can do the Laplacian for you. So, so the reason that we have to go through it by hand is really just to understand what the blasted symbols mean. I mean, just to try to understand what the notation is and what you have to do. When you can put it in Wolfram alpha, that means you have at least some idea of what the operation is trying to do. So going back to why are we going through all of this? Well, for one, Russell Humphreys is coming to talk about his paper on geomagnetism. And let me see, I have it somewhere here, Russell Humphreys, Geomagnetism. He's coming on Wednesday. Very generous of him. And there was just tons of Maxwell's equations. He was using curls, all sorts of Maxwell's equations. And I felt to honor his work, I should try to at least spool up and understand minimal amount of Maxwell's equations. So I could at least know what the equation's representing. So hopefully by then, there is this equation called the curl. And there's lots of curls. There's lots of curls in magnetic field theory. Because magnetic fields are kind of circular. And there's going to be a lot of that. Actually, this is the picture of the book. You can see it here. Be tons of curl operators. And so that's for one. The next thing is it actually, when you can do the Laplacians, these Laplacians, I'll show a better picture of this. This is kind of, when you can do the Laplacians, you can apply them to Maxwell's, to an electric field equation. And there's a little subtle exception here. So when you take the Laplacian of an electric field, you can relate it to the time varying. It's very interesting. It creates something called a D'Alembert. So you combine a Laplacian with just a little extra, and you create a D'Alembert. With the D'Alembert, you can show Maxwell's equations lead directly to special relativity. Now, as I've read the literature, was it special relativity first or Maxwell's equations? Because in the formulation of it, it's a little vague how all this came about. They wanted to have some invariance. There's some sort of invariance that they're trying to create. But if you just start, if hypothetically you begin with Maxwell's equations as they're stated, you could see special relativity. So special relativity deals with objects that are moving in relation with no acceleration. So you have velocity but no acceleration. General relativity deals with acceleration, and Einstein's equivalence theory says acceleration is the same as gravity, at least equationally, so to speak. This is funny. So the reason it's important for me to learn Maxwell's equations, geomagnetism, which is a great argument for young Earth if it holds. And then next, special relativity, understanding it, and then also looking at the possibility of variable speed of light. One would have to modify Maxwell's equations, and some theories are that you're seeing that term epsilon, where is it? You see so many terms of epsilon there, that epsilon naught, like in equation 34, appears everywhere. Epsilon naught would change. Epsilon naught would change. It may vary with time itself and also vary in space. And that is a testable hypothesis. And there's some experiments where we might be able to change the epsilon naught, the free space permittivity. Oh, I'm going to get myself in trouble. Let me make sure I got that right. Let's see. Free space, epsilon naught is free space permittivity. Boy, this is free space permittivity. It's represented, yep. Epsilon naught is the permittivity of free space, physical constant. Okay, it's measured in farads per meter. And then there's magnetic permeability, from which we get the speed of light. You get, I think, 1 over the square root of permittivity, electric permittivity, times magnetic permeability in free space equals the speed of light. Free space permittivity, permeability, speed of light. Let's see if I got this right. That is a good question. Oh, there it is. You can see it right there. 1 over the square root of mu naught, which is magnetic permeability, and then electric permittivity, epsilon naught. It says, so Ben Rex asks, does magnetic permeability also change? I think it would have to, according to that equation. And unfortunately, that's getting way beyond where I am. Who said some YEC models, you would have to have that change where speed of light would change if the 0 point energy changes. And there's an interesting paper. I mean, the nice thing about this is it could be subject to an experiment. And I'm excited that someone could try this experiment. I've also, do you remember, guys, when I showed you that interferometer I was building? People were just cringing at how ugly it looked. It wasn't my design. It was by Reginald Cahill. And he was arguing that the ether, which we might equate with the 0 point energy, could have variability, or it could have preferred direction. It could sense movement through it. So you could actually see different densities of 0 point energy. And there is an experiment that is proposed. Casimir plates. I may not be able to find it immediately. Casimir plates. Energy density. Speed of light. Here it is. I think this is an awesome. Okay, here is where we can, light velocity Casimir effect. Does the velocity of light in a vacuum increase when propagating between Casimir plates? And there have been some suggestions that it would, and let's see if they have. This is just worth touching. I'm sorry for how, oops. I'm sorry for how this looks so small. Our theory of quantum gravity, called electromagnetic quantum gravity, depends heavily on an important property of the quantum vacuum, its ability to affect the velocity of a photon propagation under two very special physical conditions. In the first place, photon propagation in the vacuum is altered when the electrically charged virtual particle density changes, as it does between the Casimir plates. And in the second case, photon propagation in the vacuum is also altered when there is a coordinated acceleration given to the electrically charged virtual particles of the quantum vacuum, such as near a large mass like the Earth, EMQG. These effects can be understood through the familiar process that photons partake when interacting with all electrically charged particles, photon scattering. Here we propose experiments that might set up to detect increase in velocity of light in a vacuum in a laboratory for the first case. That is when photons travel and perpendicular to the Casimir plates in a vacuum. So we have someone who is a graduate student in photonics. I wanted to be a grad student in photonics, God willing someday, but this is an application in photonics. I don't know how hard it would be to set up an experiment like this. So just for those who are curious, this whole thing about Casimir plates was in the discovery of the zero-point energy of quantum mechanics, Casimir. So you could look up the Wikipedia entry. There is one on Casimir, the zero-point energy. And they've said the zero-point energy has brought back the idea of the ether, which is awesome. And so Casimir. So there was this thing called the Casimir effect, where is a physical force acting on the macroscopic boundaries of a confined space, which arises from the quantum fluctuations of the field. It's named after Hendrik Casimir, who predicted the effect for electromagnetic systems in 1948. And so you heard me talking about the Casimir plates. And so the experiment is you create this, you create these Casimir plates, and then I think you can put light through here. You said perpendicular? I don't know. The speed of light is predicted to increase in that area between the Casimir plates. I don't know how that can be measured. I mean, that's a really small region. If you said perpendicular, that's like nothing. I don't know how that can be measured. If it's parallel to the plates, I could see that, but perpendicular would be kind of hard. That would be an interesting experiment to see. The only way I could think you could do that is maybe you drill a hole here and here, and maybe you get, or like here, and then get the light beam to travel that way, and then you can measure a speed change. That's about the only way I think this thing could be pulled off. But that's what the experiment was describing. So if we have, variable speed of light theories have been put on the table by professional physicists because they're trying to solve cosmology problems. So people familiar with the Big Bang, an alternate to inflation theory is variable speed of light. But if you have variable speed of light, you may not need the Big Bang at all. I just think it's exciting. But before we even get there, it's kind of nice to know this thing about Laplacians, to get all the way back to basic electromagnetic theory, especially since Russell Humphreys is going to be here, God willing, in 2 days. On Wednesday. It's Monday today. I really want, out of respect for him, to be as I'm getting these blasted notifications. Turn off all notifications for mail. Yeah, sorry about that. I have a new computer. It's just behaving like I don't have all the settings. So I just, since Ben Rex is here, it's nice having a conversation with him. And I just wanted to show the readers why we're going through this. Because we have variable speed of light. That would be good news for Yak. And good news for Yak. If the world is young, if we can show it scientifically, that would be a big boost to the Christian faith. Evidences for the Christian faith. So this is a big cross to bear because it's high risk research. It may end up nowhere, but we're trying. And I want to commend Russell Humphreys for at least trying. On the other channel at 2 p.m., it's right now about 1 p.m. Eastern. In about an hour on the main channel, Dr. Hugh Ross, who's an old Earth creationist. I have a video of Sunday worship service yesterday. And I went to King's Chapel, which isn't my normal church. McLean Bible is online. The King's, I have to go to church online because I'm not allowed in the sanctuary. But I went to King's Chapel yesterday, and Dr. Hugh Ross is preaching, and he's talking about the Earth's geomagnetic field. And I might share that clip when he talks about the geomagnetic field. I was like, Doctor, he argued it had to be miraculously created, which I absolutely agree with. And he described all of the parameters. He said this had to be so finely tuned. I'm just like, yeah, the alternative is God created it, created the geomagnetic field. It didn't have to result from a collision of the moon and the Earth. So his hypothesis is that the moon resulted from a collision that created it, that created the moon. And it was just a finely tuned collision. And it was just the right distance from the Earth that it created the circulating molten magnetic core. And the circulating core creates the geomagnetic field. It's all finely tuned. Russell Humphreys will come in and say, well, I might agree that you have circulation there in the core. Circulating charge creates a magnetic field, but it couldn't have lasted millions of years. Yeah. Yeah, just so all right, so going back to the Laplacians, there is a problem with, okay, so we talked about gradients. There is a problem with how some of the documents I read about Laplacians, how it's stated. So the gradients, you start with a scalar field, you apply the grad operator, and then you get a vector field. I think that's right. Yeah, you start with the scalar field, you end up with a vector field through that operation, and you can use Wolfram alpha to just make sure you do all your partial derivatives correctly. And that's really just beautiful because some of the even James Clerk Maxwell made mistakes, and Oliver Heaviside had to correct his calculus. That was in the old days before Wolfram alpha. So even the great ones, someone as great as James Clerk Maxwell, from whom we call Maxwell's equations, even his equations needed to be corrected so that they worked. That being said, Maxwell's equations, Heinrich Hertz, who demonstrated the predictions of Maxwell's equations, actually wanted to add one more refinement, and it's really subtle. Something to do with total derivatives versus partial derivatives. There's a Hertzian version of electromagnetic theory, maybe just for the sake, and that this is also, I'm just trying to say, consider Maxwell's equations as a pretty good approximation, but so there's this thing called Hertzian electrodynamics. So the irony is, let me see if I'm looking at this. the irony is Hertz vindicated Maxwell for the most part, but had his own version of electrodynamics. And unfortunately, let me see if I have, and then it also leads to Hertzian relativity, and there are all sorts of, there were all sorts of things that would proceed out of that. I would identify myself as a neo-Hertzian, neo-Lorentzian. If people ask me what my theological views are, I'll just say that because it just would throw them off. But there is Heinrich Hertz. He should have won a Nobel Prize if it had been awarded. There is a kind of you'll see that it's not, I don't have it handy. I barely understand Maxwell's equations. Hertz would add just a little tweak to that. It's pretty subtle. And I'm just pointing out there that the relativity, the special relativity we generate with Maxwell's equations, if Maxwell's equations are only approximation, it would have consequences for the former special relativity that we would go with. Furthermore, if that epsilon naught, the free space permittivity and the electric permittivity and the magnetic permeability change over time, as well as space, that affects things. Now, the other thing that I need to point out, people say, what do you mean by time? Okay, in relativity, time is relative and time flows differently. In quantum mechanics, you want an absolute clock. So definitely, and Sabine Hassenfelder pointed out, general relativity cannot be, it's not quite right because of quantum mechanics. Because quantum mechanics wants an absolute clock. Absolute time. One way to resolve this is to maybe, as the neo-Lorentzians, like I am, have postulated, it's not that time flows differently, it's the clocks slow down. There's a physical effect on the clock, on your measuring device, that makes it slow, it ticks down. And I like that better. I like an absolute time with clocks that just slow down. So clocks slow down if you accelerate for a long time and you gain a lot of velocity. That's one. That's a special relativity effect. And then gravitation. So how does it go? Low is slow. So when you're in strong gravitational field, your clock will tick slower. When you're far away from it, your clock ticks faster. So low is slow, which means low on the earth. High, you fly. Okay. Someone actually taught me that at the Creationist Conference 2 weeks ago, down there in Tennessee, because I was always getting it backward. So I know, guys, this is painful. Physics is agony. Biology is easier. Criticizing evolutionary biology is really easy compared to this. So anyway, so I just mentioned we're trying to go through Maxwell's equations, and we're trying to get the Laplacians. And so that's the next topic. So let me show some of the problems. Let's see, vector multivariate calculus. So we went through the gradients, and since we already did divergence earlier, there is divergence operator. There it is. The point form of Maxwell's equations is the divergence of an electric field is equal to the charge density. So you see this operator div A. Now let me show you that. Really, you can just take that and it's the first of Maxwell's equations. There you have it. In that case, it's div D equals rho v, which is the charge density in a point volume. And D equals epsilon E, or did I get that backward? See if they have it. There's something about D and E, and I better get that right. Well, I'm going to get this. I'm pretty sure there it is. Equation 2 on page 55. D equals epsilon E. So if you have an electric field vector space, you multiply all the points on that vector space by epsilon naught, and then you get the D vector space. And then the D vector space, if you take so that was page 55. After a while, it gets crazy because you keep referring to something so much that you start to remember the page numbers. And it's really bad when they change the addition on you, because then all the page numbers are all changed. But then the divergence. So the divergence of D, remember D is epsilon naught E. The divergence of D equals the charge density. And we had it's really flux density. Hi, welcome to our nerd torture session. We were just talking about how all this related to Yek, and we're going through the gruesome math. It's across the bear. Let's see, in German, we do a simple saying to make us remember it better. We call that a donkey's bridge. Okay, donkey's bridge. So I needed my donkey's bridge there. So this is the significance of the divergence operator. And this is really agony, guys, because it's like we're doing all this math and it's like, does it get us anywhere? Not really at this point. It's only when we get up to much higher levels that we start to even be useful, like being able to do analysis of let's say we wanted to make a motor. I remember when I was in electrical engineering school, I said, Dr. Cook, I'd like to make a motor. He said, that's not trivial. And I was afraid I was going to hear that from you, sir. Because you can make a motor, but if you want to control its characteristics and make them as optimal as possible, like the number of windings and stuff with the wires around all the metal parts, etc. You'd have to be doing Maxwell's equations and doing this at the graduate level. And he said, he said, you wanted to do what? I said, I wanted to make a very lightweight motor from scratch. And I'm glad he didn't laugh. He said, that's non-trivial. Because if you've ever taken apart a motor, like these little toy motors, Mabuki motors, they're beautiful. I used to buy these from Edmund Scientific. And I was just so excited. I had this battery connected to the motor, and I would modify the motor, just change the windings. And I'm like, this is really cool. And I'm like, okay, I don't know what I'm really doing when I'm modifying the motor. I said, I'd like to learn how to do this professionally. And I actually talked to a graduate student. I said, what did you study in graduate school for 2 years? He said, motors. And I'm like, did you have to do lots of Maxwell's equations? He said, yes. And I'm just like, oh. So making a motor, if you have a pre-designed diagram, yeah, that's probably not too bad. But to understand how to actually make the design is agony. Maxwell's equations are agony. You just have to go through stuff like this. And I could just imagine the poor guy trying to kind of understand this and make a contribution. Now, in the era of computer-aided design, yeah, it's going to be a lot easier. Oh yeah, here you go. There are a lot of simplifications which can give you a good approximation, which get you quite far. A friend of mine is building a power transformer. So, a lot of transformers, you just have metal and lots of wires. Metal and lots of wires, you're thinking, how hard can that be? And it's like, it could be pretty hard. It can be pretty, it's not trivial. I mean, you can make some of these nice AC transformers that are when you're not dealing with too much power. But when you get to power transformers, there are safety issues. Like I live near a transformer and that thing has exploded a few times. I mean, not that it would endanger my household to my knowledge, but I've had transformers burn out in the house. So even moderate power, that'd be interesting. And he said he went to the same. So I didn't know that he didn't do too much. So I know that he didn't do too much Maxwell. Oh, that's the interesting thing. He didn't do too much Maxwell's. So there may be rules of thumb where you don't have to get down into that. Now, I think a power transformer, there's safety issues and materials. And sometimes you can just boil it down to the number of windings if you want to do step up, step down, etc. he wants to have the biggest one, which you can run as a private person, and he way over engineers it. 400 volts and 32 amperes. Oh man. That would be what, 12,000 watts? 12,800 watts. Is my math right, Ben Rex? That's a lot of power. I'm curious, what would his application be? 12,000 watts. Yeah, that's about the household. Yeah, I think our limit here in our neighborhood is around 20,000 watts. Every house the circuit breaker will blow when your whole household is using about 20,000 watts, which we never blow the master circuit breaker. The only it does make sense that if you have an electrical storm, so much could come through inadvertently, and it would trigger the 20,000 watt circuit breaker. I think circuit breakers are rated in amperes because there's an assumed voltage, something like that. 12,000 watts is still pretty big. So again, just going back here, so we can, the math is there, the divergence, it can be done. So the next topic is the Laplacian. And like I said, a lot of this is just understanding the symbology and knowing how to put what where. I mean, this looks just like brutally ugly, but a lot of electromagnetic theory is, and as Bertrand Russell said, a lot of mathematics is understanding the symbols, understanding the symbols. So if you have the symbol of the equation, you have to know how to apply these operators like the Laplacian on it. And then so you have an equation, you apply an operator to it, and then you make another equation. If you can just get the accounting right, then you're doing good. And then translating it into what it means in terms of physical significance, that's when you kind of roll your eyes and just like, okay, the math wasn't too bad, or it was tedious, but then when you try to visualize what it means, that's when you kind of rack your head, you rack your brains. It's hard. So I need to point out something in this document, and then maybe we'll wrap it up. So we have this thing called the Laplacian operator. It's the div grad u, and you don't have to care about that. In Cartesian coordinates, it just boils down to this. The second partial derivative of your equation, and it says it's a scalar field. It's a scalar field. Now, I need to point out something that I just learned, and this is where I got really upset because you go over the internet, most of the time they say the Laplacian applies to a scalar field. I found a document, And yet when I tried to do special relativity, deriving special relativity from Maxwell's equations, they're applying the Laplacian to a vector field. And I'm just like, and I thought I was getting so close. And then I went over, I mean, guys, I spent 4 hours trying to track this down. And I said, there's a vector Laplacian, and then there's a scalar Laplacian, and then there's a scalar Laplacian applied to a vector field. I was just, one reason I was late this morning is I was just scratching. And I said, okay, whatever you call it, tell me how to make the operation work. Show me how to do, again, a lot of this is just like you're given an equation, you're given an operator like an Laplacian, you come out with another equation. Just show me how to kind of do the mechanics. And so it ends up just be kind of, taking stuff off the shelf and putting it and relocating it, or taking it off the shelf, modifying it and putting it in another shelf. And I learned to do a lot of math just kind of doing it that way, just kind of rote mechanical. And then now that we have Wolfram Alpha, it does it even better. You just have to know, it used to be you put, in the computer era, you have input, you put it in the black box of the computer and it outputs. So they say garbage in, garbage out. But if you put it in right, good stuff in, good stuff out, assuming your computation is right. In the old days, you had the input and you had to act like the black box and make the output. So you had places where you could really fail. Now, I found this out when I was studying mathematical physics. In the good old days, before they had modern day computers to do all this, when like Richard Feynman or someone wanted, some scientist wanted to do a computation, they'd have what they call calculators, human calculators. So they'd have a line of mathematicians, that knew how to do this. And the guy said, okay, do this derivation. And it'd be a pipeline, like a factory pipeline. It's like one guy was really good at doing this kind of manipulation, and it'd be handed off to the next guy and handed off to the next guy. And you could see that for old days physics, if we're going to do this, you would need, you would actually want to assemble a team that could do stuff like this. And I would presume you would want to have it cross-checked by another team because it's too easy to make these mistakes. And yeah, the danger is that the black box does something wrong because you configured it wrong. Yeah, and so that's why, we're hoping Wolfram Alpha gets it right for at least the basic stuff. There was one instance where a mathematician found a flaw in an Intel chip in doing numerical calculations. It was a really subtle rounding error, and the mathematician was really sharp. And Intel had to do like a recall or readjustment or an apology. So it worked well for most applications, but there's one subtlety where the Intel chip had a problem. So, I'll tell you at this point, my math skills are so rusty. I think the computational tool, if I see a disagreement, I would probably redo my math at this point. And last but not least, I have a book called Abrahamowitz and Stiegen. It's a book like this. Maybe I ought to get it because it has all these integral tables and derivatives. I mean, it's like $100 book. My teacher said, okay, guys, open book test. And he said, okay, I take no offense. When I put a problem on the exam, you can do it by manually, like I showed you. But since this is open book, if you want to bring Abrahamowitz and Stiegen, you can bring it with you. You can bet I bought that book and I brought it just to get through that because I knew he already forewarned us we were going to have one exam question. And actually, if you give me a second, I got to show off this book. Oh, well, I misplaced my Abrahamowitz and Stegen. So this is bad. The most difficult exams are the open book ones, which you can even use Google. In those cases, you know nothing will help you besides what you understand. Oh yeah, mathematical physics, they were open book. And it was, I would say it's the second hardest class I took in graduate school. The hardest class, ironically, was classical mechanics. They're doing stuff like Hamiltonians. And the thing that was killer was all these coordinate systems. It was just miserable. You know, because you're trying to visualize things in 3D space, and you're also doing velocity. You have these 6 degrees of freedom. It was tough. I think I'm still traumatized from that experience. So anyway, going to this Laplacian, they say it's a scalar field, but I found this. I'm so glad I found this. It says here, the Laplacian operator can also be applied to vector fields. For example, the equation 4.10.2 is valid even if the scalar field f is replaced with a vector field. In the Cartesian coordinate system, the Laplacian of a vector field A, where the vector field A is defined as that x hat is the, let me get over here, that x hat is the unit vector for x. It's like I. So you have ijk, or you could say x hat, y hat, z hat. I don't know which is better. Anyway, oh my goodness. Oh, Rebecca, you're here. So you have this x hat, and then you take the Laplacian of ax. So the coefficient of x hat, you take the Laplacian of that, and then same for the Laplacian of y and the Laplacian of z. But the thing is, and then you reconstruct it and you get a Laplacian of the vector. You get a vector in the end. And so let me go over here and compare it with how they do this. Here, you don't end up with a vector, you end up with a scalar. So there's a scalar Laplacian applied to a vector field. And this is really kind of funny because there's a vector Laplacian that you apply to there's a vector Laplacian and a scalar Laplacian. And then you use the scalar Laplacian on a vector field, which is kind of funny sounding. So let me see. Vector scalar Laplacian. The vector Laplacian is just miserable looking, and that's not what we're gonna use for electromagnetic theory. But just for, see, this is the vector Laplacian where you have a curl. You have a curl of a curl, and that's not what we want. We want the scalar Laplacian, which, let's see if I can find it, the scalar Laplacian. And this is where I got so confused. I was just so unbelievably confused. The scalar Laplacian. This is the scalar Laplacian here. You use a scalar Laplacian on a vector field, and that's what you want in electromagnetic theory. You don't, to my knowledge, you don't use the vector Laplacian. Anyone out there can please correct me. You don't use the vector Laplacian. Let's see. You don't use the vector Laplacian for that. So you take the vector Laplacian of a vector field, but you can also take the scalar Laplacian either on a scalar field or a vector field. You use the scalar Laplacian, in fact, we just call it Laplacian, on a vector field as according to what this document said. And I'll show you the significance of that. And this is, guys, I was just agonizing over this for hours trying to, it's just like, this is going to kill me. Because I ended up on Swami Das's website, and the guys were just giving me a hard time. And I was just showing them, it's like, you know, I'm willing to just mix with this and learn from it. And I think it blew over the heads of just about everyone. But I said, we're trying to solve the distant starlight problem. I'm going to try to show some things about this. And I said, I just want to show you I do understand some of this. My math is really rusty. But anyone in the comment section, I'm hoping I get professional physicists. Oh, you know, Russell Humphreys is a professional physicist. He works with Maxwell's equations. These would be kind of like nice side questions to relate to him. And we could have a nice, so he's a professional physicist. So Russell Humphreys, who's coming on Wednesday, could help with some of this. But just to show where all this was going, I was on Swami Das's website, and this is rolling. This was blowing everyone away. I said, this is still important if we're going to try to solve young Earth creationist problems. So you could see the my computer. So I was having something as basic as like, should I put an arrow over here, which means to emphasize it's a vector. Usually if it's in bold print, it's a vector. And I actually missed the vector here. So this is a vector. So this is a scalar Laplacian applied to a vector field, and a partial derivative applied to a vector field. And so what does this equation here? This is the electromagnetic wave equation, or something like that. Electromagnetic wave equation. This, so when we took Maxwell's equations, okay, so guys, I'm going to just go back up. When you're dealing with single variables in differential equations, single variables, you know, where it's x and f of x versus, you know, f of x, y, z, that's multiple variables. We're just doing f of x. You can have differential equations where you have f of x related to its derivative. That's a differential equation. And they call that ordinary differential equations. When you have multiple variables, it becomes partial differential equations. And I actually didn't know. I mean, I knew about partial differential equations. I didn't know what the word ordinary meant. That's just, they said, you know, it's the number of variables you're dealing with. So partial differential equations, you have to find solutions. So you have the equation, but you don't necessarily know the solution. So what that means is you may have an equation that relates f of x to its derivative. So a real easy one is like f of x equals derivative of f of x, or f prime of x. So f prime of x is derivative of f of x. So if you say f of x equals f prime of x, you have to look for a you have to look for a derivative. You have to look for the function that will meet those requirements. And I think a simple one is e of x. So just because I'm kind of rusty on my math, let's do Wolfram alpha again. And I'm just going to guess here. So we want here calculus and analysis, and we'll do derivatives just for right now. There's probably a section on differential equations. So it's to calculate the derivative of a function. So I'm going to just say e of x, b dx e of x. And the derivative is e of x. So solution to the differential equation f of x equals f prime of x, one solution is e of x. So there must be also another ordinary differential equation. Let's see if they have one here. Integrals, derivatives, do they have differential equations? See if they have anything on differential equations are nasty. They can get. So let's do a differential equation. Oh, there we go. Ordinary differential equation. So let's say y equals y prime. And should say e of x. There. Oh, here's solution. There you go. C1 times e of x. You can put a C1. The most general solution is you have an unknown coefficient. So these are ordinary differential equations. So how does this relate to what we're talking about with special relativity? You have the second order partial differential equations of Maxwell's equations. I think they're second order. I'm sorry, guys. Let's look, see if they are second order. Maxwell's. Let's look. The way you could tell is if the derivatives, okay, let's look at the differential form. They look like they're first order. They look like they're first order. Because you have a derivative with respect to t. These are partial derivatives. So you have the divergence operator, which is first order partial derivatives. Let me pull out my book. I think they're first order partial differential equations. I think Schrodinger's equations are second order. We'll see. Okay, so I'm looking at my electromagnetic theory book right here. First order derivatives. First order derivatives. The only second order derivative is I see with the Laplacian, but you don't see any Laplacians. I don't see any Laplacians here. So this is first order partial differential equations. You take the set of all this and you can predict an electromagnetic wave. The solution to this, solutions to Maxwell's equations are electromagnetic waves. That's what Heinrich Hertz was able to, and a lot of those geniuses figured out. He said that those are ugly differential equations. So you saw, like, I took a first order ordinary differential equations, like f of x equals f prime of x. The solution to that is e to the x, or c times e to the x. So you can have the differential equation. You don't know if you can get a nice, tidy solution to it. Hopefully you have something that's tractable. Then you go to the world of partial differential equations, and these are first order partial differential equations. is it possible to compute a solution to that set of equations? And the solution is, I showed it earlier, the solution to Maxwell's partial differential equations, one of the solutions is this one right here, where you take the Laplacian of the E field, and it's equal to the second order derivative of the E field. I mean, that looks innocuous enough. It took a genius. It took some geniuses to figure that out. Okay, guys, that may look compact and innocuous enough. I imagine this was just like brutal. I mean, I think these guys probably spent years on that. That you know, just like E equals MC squared. It looks innocent enough, but to actually figure this out was probably years. Years to figure out this equation. This equation here this is a lifetime of work to figure that out. And I mean, to have a starting place where you start, this is your starting place here, Maxwell's equations. This is your starting point here, Maxwell's equations, and they're differential equations, which means you don't actually know the form of, see, this E here, we actually don't know the form of that X, Y, Z, and T. We don't know the we don't know the form of it immediately just from these equations. But the nice thing, guys, is this Laplacian that I showed earlier. You see this? I'll show you. You want me to show you a solution? This is so, it looks, that's the solution. The sine wave. All that agonizing math can resolve to one solution is a sine wave, which is really nice. And so, you know, the way, and you know, with Fourier transforms, you can add various sine waves together, and it'll actually also be a solution. If one sine wave is a solution to the differential equations, then other sine waves can be, and then you add those, and the summation of all those can also be solutions. So this is with all that agony, it's really nice that you can, that's why Fourier was such a breakthrough, that we could decompose really tough things into just summations of sine waves, which was great. So how does this relate to relativity? And we're about to start on Hugh Ross's stuff in about 15 minutes. We play with these Laplacians, and at some point I'm going to go through all of the Laplacians. You could see here I'm setting up the Laplacian, and you combine it with one little term, this term, this 1 over c squared. See, I modified this original equation a little bit here. This one here, this is equal to 1 over c squared. And so I modified it, and you get, this is just algebra at this point, you get this equation. And this looks, if you take out the e's, you get the D'Alembert operator. And when you work through all of this, and I did the derivation here, when you work through all of this, and it's just grueling, when you work through all of that, you end up showing special relativity. And at some point, I'm gonna write a educational paper where you actually do this derivation here. And like I said, the nice thing is we have Wolfram Alpha to kind of help us get all this correct, because it gets very unwieldy. There's so many terms. As I was working this out by hand, and this took me a long time to work it out by hand. I mean, just look at that. Look at this. I did this. I worked this out by hand. Okay. As you can use, I didn't use Wolfram Alpha for that, but if I needed to fall back, I could. But I mean, this was just grueling. I mean, it's just tedious. It's, it take a couple hours to start to construct all the terms. And then it's just knowing how to add things up to make it look right. And then you can get the Lorentz transformation right here. You start to see the Lorentz transformation, which is relativity. And then now you can start to deal with speed of light. But, oh man, that was just grueling. It's grueling, it's tedious, but it's kind of nice to say you could start off with electromagnetic theory like that. And you can mathematically connect it to special relativity and this phenomenon of time dilation. I prefer to call it clock slowing rather than time dilation. You could just throw all this in here and you can connect, electromagnetism to special relativity. And that begins, that connection is built on being able to do Laplacian operators of electromagnetic theory. When you can apply those Laplacian operators to Maxwell's, to electromagnetic theory, you can then start to derive the importance of the Lorentz transformation, which leads, the Lorentz transformation gives you the relationship between the clocks in moving reference frames. And you can see time dilation, or what I prefer, clock slowing is a better term in my opinion. And it was exciting because we have confirmed it experimentally that the clocks slow down. We had these atomic clocks, a variety of them, either ones that we built or maybe those in nature. And we've been able to demonstrate the clocks slow down, which is amazing. Why they do, I don't think anyone knows. But we are able to at least predict it if we assume Maxwell's equations for electrodynamics. Just beautiful. And you get all these mysteries of the universe. So anyway, Hugh Ross will be coming on in my next channel, and I'll just be like attending to the house and taking care of things here. I will be in the side chat. Glory and honor to our Lord and Savior Jesus Christ. I'm really looking forward to hanging out with you all as we watch Dr. Hugh Ross. Let me put a link to that. It's not going to be on this channel, but let me put a link to that on in the side chat. So one moment. It was a great worship service yesterday. I was so blessed. I mean, he's just a great human being, a great scientist. He converted Nobel Prize winner Richard Smalley. He and James Stewart witnessed to Richard Smalley. Richard Smalley became a Christian. So astrophysicist, Reverend Hugh Ross, God bless him. It's great to have a pastor who's also a physicist, an astrophysicist at that. I think that is just so cool. So with that, let me bring up the closing credits. And I'm just setting it up. Let's just finish off with some Rachmaninoff just to soothe your nerves. God bless you all. The grace of the Lord Jesus Christ be with your spirit.